So today we're going to talk about, or finish talking about Chapter 10 in probabilities. From the previous lesson, there are two big takeaways. We have a formula to calculate the probability for combined events, which was this. And as a special case of this formula, if our events are mutually exclusive, i.e. that the intersection of those two events is empty, we can say that this simplifies down to just P of A plus P of B. Again, if this is empty, the probability of drawing something from there is 0, right? So this was kind of the big takeaway formula-wise from last time. Today we're going to start by talking about independent events. So we define two events as independent when the intersection of the two events, or the probability of the intersection of two events, is equal to the probability of the product of the two events. So an example of independent events, let's say we're flipping a coin and we're playing a game and you're trying to guess whether this coin is going to be heads or tails. Let's say I've flipped the coin 10 times so far this game, and every single time it's come up tails. Which is more likely to come up next, heads or tails?
You don't know. 50-50.
Good. So it's still the same probability as it was before. It's still 50-50 because flipping a coin is an independent event. The 10 flips before have no effect on what the next flip is going to be, right? To think about it otherwise is called the gambler's fallacy. So if you've ever been to a casino, not all of you are too young, so probably not. But if you ever go to a casino, particularly when the game roulette is being played, like you can see they have like a big list, a board of like what the last 10 or 20 spins have been. And you'll see people, like if the last 20 spins had all been red, lots of people flock to bet on black, thinking that, oh, black must be due, and it's not that way at all. Like, roulette is independent. It's still the same probability of it coming up black this time as it was for all 20 of the previous spins. Example of an event that's not independent? No. Dice are independent. I would say drawing cards out of a deck. So if we draw, so let's say that we're trying to draw hearts out of the deck, okay? And we draw the first card, and it's a heart. The probability of drawing the next card is going to be different because we have a different total number of cards and a different total number of hearts in the deck. Correct. Without replacement, this is now a dependent event, where the outcome of the next draw depends on the previous one. Is everybody okay with the idea there of dependent versus independent events? So let's kind of continue on. So that was like 10-6. 10.7, we're going to stop and do several examples. 10.7 is about tree diagrams and Venn diagrams. And we're going to stop and do some examples in here because it allows us to kind of connect a lot of these ideas and formulas that we've used so far together. Yes, sir? Sure. Okay, so let's consider the following example. Let's say we have a bag that has 5 red marbles and then 3 blue marbles. We're going to draw a marble, put it back, and then draw a second marble. So this is a good example of a problem where drawing a tree diagram could be helpful to us. So there are 2 events that take place. So the first event is drawing the first marble. What are the 2 possible outcomes of that first draw? You could get a red, or you could get a blue. What's the probability of getting a red marble? 5 out of 8, because we have 5 reds and 8 total. And the probability of a blue? 3 out of 8. Now, assuming that we draw a red marble first, what are the 2 possible outcomes here? Still red or blue, right? So draw 2. And the probability of drawing the second red marble is? Still 5 out of 8. Why? Because we put it back. And the blue is still 3 out of 8. Now let's look at, hypothetically, what if we drew a blue for the first one? The 2 possible outcomes are still red or blue, and the probabilities of each one is still the same, right? 5 out of 8, 3 out of 8 respectively. So we could ask questions, what's the probability of drawing a red and then a red? So which path of our tree diagram is that going to be? Red and then a red again. Everybody agree with that? So is drawing these marbles independent event? Yes, right? The previous draw has no effect on the next one because we put the marble back. So this is just going to be the probability of drawing the red times the probability of drawing the red, or 5 out of 8 times 5 out of 8. Everybody okay with that? What if we have the probability of drawing a red, then a blue? So if I look at my tree diagram, that path is that one, correct? And again, these are independent events. So I can just treat them as multiplication problems. Everybody agree with that? Where this could get a little trickier is if I ask the probability of drawing if I just want the probability that I've drawn a red marble and a blue marble, regardless of the order. So you'll notice that there are 2 ways this could happen, correct? We could draw the red and then the blue, or we could draw the blue and then the red. Everybody agree with that? So the verbiage here matters a little bit. So this is like red-blue or blue-red. Everybody agree with that? Since these events are mutually exclusive, I can't draw a red and a blue marble at the same time. I can use my probability of are mutually exclusive, to rewrite that union as the sum. Everybody okay there? And then since these events are independent, I can do that. And now I can say 5 out of 8 times 3 out of 8 plus 3 out of 8 times 5 out of 8. Everybody okay with that idea? So really for this problem, because of the replacement, we didn't really need the tree diagram, although it was helpful to kind of visualize what was happening. It wasn't as necessary. Let's look at a slight modification of this problem where the tree diagram becomes a bit more useful. So let's say we still have the 5 reds, we still have the 3 blues. We draw, keep it, and then draw again. So again, in our first draw, we have 2 outcomes. And nothing much has changed there, correct? So let's say, hypothetically, on our first draw, we've drawn a red. The second draw has 2 outcomes. You could get a red, or you could get a blue. What's the probability of drawing a red now? 4 out of 7, because we've kept that red marble out of the bag. The probability of drawing a blue is 3 out of 7. Again, because there's 1 less marble in the bag, and that marble was a red one. The same thing can happen here. We can have a red or a blue. The probability of drawing a red now is, you mean 5 out of 7? Because all the red ones are still there, but there's 1 less marble. And the probability of drawing the blue is 2 out of 7. Everybody okay with this picture? So if I wanted the probability of a red and then another red, that is going to be this path, right? Or 5 out of 8 times 4 out of 7. If I want the probability of drawing red, blue, I'd want to do this path, right? If I want the probability of just the 2 marbles let's just say 1 red, 1 blue. Just write it that way. Notice there's 2 ways to get that still. So you can have blue then red, or you can have red then blue. So we have something like that. Again, these tree diagram problems are some of the IB's tests' favorites. It seems like every set of tests, either on test 1 or test 2, there's a tree diagram probability question on there. Let's do one more. So this is from page 313, example 10.9. And it says, if the weather is fine, Mr. Liu walks to work. The probability that he's late is 0.1. If it rains, Mr. Lou rides the bus. To work. The probability that he's late is 0.3. The probability of rain is 0.45. So let's start by drawing a tree diagram to kind of see what's going on here. We have two decisions to make, right? Whether he's going to ride the bus or walk, and then whether he's going to be on time or late. Everybody agree with that? Which one depends on which? Yeah, which one depends on which? The mode of... Well, I was going to say that the first decision we need to make is whether we're riding the bus or walking, rather than whether we're on time or late, right? We need to know which mode of transportation we took in order to figure out if we're on time or late. Do you guys agree with that? Okay. So the first decision is going to be his mode of transportation. And if we are, so we could either be walking, that happens if there's no rain, or we could ride the bus, and that happens if there's rain. Everybody agree with that? What's the probability that we are riding the bus? 0.45, because that's the probability that it rains. What's the probability that we're going to walk? 0.55. Why? Yeah, exactly right. Claire? Sure. Okay. Now, from walking, either we're going to be late or on time. What's the probability that if we walk, we end up being late? 0.1. So the probability that we're on time then is 9. So if we're riding the bus, what's the probability that we're late? And then we're on time. Everybody good with that? So we could say the probability that we ride the bus and we end up on time, so that would be 0.45 times 0.7. Everybody agree with that? Or we could just, we ask the probability that we're on time. So notice that there are two paths that end up on time, correct? There's this one and this one. So this is the probability that we are walk and on time. Or that we bus and are on time. Since these are mutually exclusive, we can't walk and ride the bus at the same time. We can break these up and then apply our independent events property to do this. So we have 0.55 times 0.9 plus 0.45 times 0.7. Let's look at some Venn diagram examples now. So this is from page 316, and this is example 1010. It says that we have 95 IB students, 45 study bio, 39 study French, and 24 study both. So this seems very much to me like a Venn diagram kind of question. It sounds a lot like the Venn diagram questions we had from the previous chapter. So maybe I'll start by drawing myself a Venn diagram. Yeah, except it's Friday. TBF. Yeah. So when we fill out a Venn diagram, what part do we want to fill in first? The middle. And what goes in the middle? 24. That is the numbers that go there. And now how about the just biology part? What number is going to go there? Which is 21. And the just French part is going to be 15. 39 minus 24. But I thought there's supposed to be 95 total people, and we don't have 95 drawn here. The rest of the people must be doing neither. Everybody agree with that? Okay. So from this, we could ask for like the probability that we study bio or French. We could do this two ways. So we could do this as a combined event problem. So that would just be the probability of studying bio plus the probability of studying French minus the probability of studying bio and French. So that's 45 out of 95 plus 39 out of 95 minus 24 out of 95, which equals 60 out of 95. The other is you could do this using the Venn diagram, using mutually exclusive events. So what do we mean by mutually exclusive? It means the sets that we're going to consider have no overlap. So I could take that set, and then that set, and then that set separately, because those are all in the bio union French. Everybody agree with that? So I could think about this instead as 21 over 95 plus 24 out of 95 plus 15 out of 95 still gives me the 60 out of 95. So either way of thinking about that is okay. Not a big difference there. How about the probability that we study not biology? Well, there's kind of two ways you could do this. I think the easier is using the complement formula. So the probability of not biology is 1 minus the probability of biology. So you could do it that way. Or you could do it using thinking about mutually exclusive events and using the Venn diagram. So the probability of not biology, oh, I should have picked, So I would do, that's not in the biology circle, and that's not in the biology circle. So you could also do it as, yeah, and again, like, that's why I am trying to show you lots of different ways of kind of thinking about it. Some of them use the picture a lot. Some of them don't use the picture at all. It's kind of about what you're more comfortable with. There's usually, when probability is concerned, lots of ways to kind of skin the cat. So it's about finding a method that you feel good about. The recycle bin used to be over there, but I put it in the hallway because nobody was recycling it. So 10.7 is about probabilities with replacement, without replacement. So we've already done this. So if you just look at the marble example that we did previously, that is a very nice example of with replacement, without replacement that we've already done. So rather than take more time here, I'm going to kind of just bypass that. We'll come back and do a bunch of examples on Monday once everybody's back, but it doesn't get tremendously more complicated than what we just saw. The last one is on conditional probability. So the way that we write a conditional probability is we write it like that, where this is just a vertical line. And what this means is the probability that A occurs given that B has already occurred. So let's look at an example problem here involving some of these conditional probabilities. So this is from page 323, example 10.11. Zoe has 5 pink socks and 7 blue socks. Without looking, she picks a sock and puts it on, then picks another sock and puts it on. And yes, Zoe's a big weirdo who has odd numbers of socks. Yeah, they're probably in the crack between the washer and the dryer, probably her missing pink sock and blue sock. Or maybe she already wore a mismatched sock pair the last day and they're in the dirty clothes now. Oh, they always end up in my pants. When I get a missing sock, they're always like stuck in the inside of a pant. Like I'll put on a pair of sweatpants and be like, this feels weird. And it's a sock. And then I'll go, oh, there's that sock I've been missing. Okay. So to me, this seems like a natural problem to draw a tree diagram for. Because again, we're making kind of two decisions like that. Everybody agree? Okay. So the first decision, the two outcomes would be pink sock or blue sock. What's the probability of getting a pink one? And the probability of getting a blue sock? Now, if we've drawn a pink sock, there are two possibilities. We could either get another pink sock or a blue sock. The probability of getting another pink sock would now be 4 out of 11. Why is it changing? Yeah, we put that sock on. Okay, and the probability of the blue sock is 7 out of 11. Remember, the sock that's missing, we know, is a pink sock. So all the blue socks are still there, but we do have one less sock to choose from. And then if we look at the other option where we've drawn a blue sock first, what's the probability of picking a pink sock? 5 out of 11. And then the probability of picking a second blue sock is 6 out of 11. Everybody feel good about finishing that tree diagram? Okay. So, let's just calculate the probability of a matching pair. What are the matching pairs? Well, that could be pink, pink, or blue, blue, right? So that's just going to be the probability of getting a pink and pink, plus the probability of getting a blue and blue. Since those events are mutually exclusive, you can't get a pair of socks that's both pink and blue at the exact same time. So the probability of pink, pink is 5 out of 12, 4 out of 11. And the probability of blue, blue is 7 out of 12, 6 out of 11. Everybody agree with that? Okay. So what if we're asked, given that she picks a matching pair, what is the probability it's a blue pair? So the key word here that kind of cues me that this is a conditional probability is this kind of given, that you're told that you're assuming that one thing has already happened and now finding the probability of the second thing. So ours is probability that we have a blue pair given that we have a matching pair. Everybody okay with that in terms of my setup? Now if I apply my conditional probability, that's going to be the probability that I have a blue pair intersect the matching pairs divided by the probability of a matching pair. Everybody okay with that? Okay. You can use that equation for every conditional probability. So what is blue pairs intersect matching pairs going to be? So I have the set of all matching pairs, right? What's in that set? Blue, blue, and pink, pink, right? Everybody agree? And then I have the set of just blue pairs, which is just blue, blues, right? The overlap of those two is going to be just the blue, blues. Everybody agree with that? So this is really just the probability that we have a blue pair over the probability that we have a matching pair. Everybody agree with that? Okay. So the probability of getting the blue pair, well, we did that inside of the previous problem, right? It's just that. You could do it again, but it's sitting right there. And the probability that we have a matching pair, well, we did that in the previous problem. That was the whole thing. Again, you could write it again, but I don't want to. See, we probably have time to do one more example. Let's do another one. How's that sound to you guys? All right. So this is page 325, example 1013. It says 100 members of the film club are asked which type of film they like watching, animation, thrillers, or romances. And, oh, we're given the Venn diagram in the problem. That's rather boring. I thought we were going to have to make this. So here's A for animation, T for thriller, and R for romances. Let's just, what would I do right quick before I get going? Yeah, I'm just going to add them up real quick and make sure that I actually get 100 because, I mean, it probably does, but, so let's see, that's 30, 60, 78, 100, so I got everybody. Apparently nobody's favorite film is science fiction or something. Okay. So let's say we asked, what is the probability that someone likes the animated films? So how would I do that? Is there anything conditional to this probability? No, right? It doesn't say given that something else. So all I need to do is just get the number of things in the animated set divided by the number of total things. 12 plus 11 plus 6 plus 12 out of 100. I think that comes out to be 51. Why did I pick all of those things? Yeah, I had to look at the entire A circle, right? And this was actually supposed to be a 22. I just wrote it down wrong. My apologies. I think I counted it as 22 when we counted them, but apparently 2 minutes later I couldn't read my own penmanship, so it's always a good sign. So part B, it says, given that they liked watching animated films, what is the prob they also liked romances? So here, this is a conditional. What word in there kind of cued us that? So if you're told that we assume that one thing has happened, then find the probability of a second thing has happened. So we would have the probability of romances given that we like animated. Everybody agree with that? So when I put it into my formula, that's the probability of R intersect A divided by the probability of A. Everybody agree there? Okay. So we know the probability of A already. We did that in part A. Let's go look at R intersect A now. So R intersect A is this piece. Everybody agree with that? So that's 18 out of 100. And that reduces down to just be 18 out of 51. Do we feel okay on doing these? They're not so bad.